Good afternoon. My name is Neng, and today I'll be presenting on my FYP study on attacks against federated learning, or FL for short. For my presentation, I will first introduce my FYP, then go into the basics of FL, some attack and defense methodologies, experimental results that I've collected, and finally conclude. So, federated learning has become very popular among businesses, especially amongst those who have been hit by the increasingly strict data privacy and protection laws before. This project aims to study some attack and some defense methodologies that can be used on FL. Due to the limited time frame of this project, the objectives are narrowed down to just one attack and one defense methodology. I will begin by briefly talking about the basics of FL. FL involves two main concepts: collaborative learning and privacy preservation. Collaborative learning pulls the user data from the devices of the users from different organizations, then use the pool to train the globally shared model, G, from time t to t+1. This implies that user data must be sent across the unprotected World Wide Web to the central server, where the global model will be trained. So, this makes the user data vulnerable to interception attacks and leaks. However, FL also demonstrates privacy-preserving capabilities. This is done by training the model locally with the user data first, then pooling the individual model updates at the central server. Hence, user data will never need to leave the user's device. This guarantees privacy preservation, but only with the assumption that user data cannot be inversely derived from model updates. Now, after covering the basic ideas of FL, I will discuss about some attack methodologies investigated in this project, specifically the distributed backdoor attacks. Before that, we need to understand what is a backdoor attack in machine learning. It refers to a data poisoning attack which is centralized in nature to only each malicious participant and aims to inject codes to synthesize backdoor triggers on some targeted data that will trigger a change in class labels of those data during model training. Targeted data can be a set of data belonging to the targeted class. For example, all data with class label 8 will have their labels changed to any other random class labels. Targeted data can also be just a random set of data. For example, all the data in a random set will have their labels changed to class label 8. The backdoor model will be conditioned to predict wrongly the class labels for test data where the backdoor trigger is present. In centralized backdoor attacks, each malicious participant will synthesize the same backdoor triggers into their dataset during training. This is the baseline attack implemented by the base code provided for this project. In distributed backdoor attacks, the backdoor trigger, which is now called the global trigger, is decomposed into simpler local triggers. Each malicious participant will then choose only one local trigger to synthesize onto their local set of targeted data during model training. This implies that at least one of the local triggers present will trigger the backdoor attack. Even some composite triggers, like the global trigger, which were unseen in the backdoor dataset during model training, will trigger the backdoor attack. According to some researchers, distributed backdoor attacks still outperform the centralized one significantly when evaluated using the global trigger. Now, I will discuss about the defense methodology that this project has investigated and even implemented, which is the Poisoning Defense Generative Adversarial Networks, or PDGAN. Before going into PDGAN, recall that backdoor attacks are central to malicious participants. On the contrary, defenses are deployed where model updates are pulled, which is usually at the central server. Current defense mechanisms focus on identifying anomalous model updates, as model updates are the only inputs available from the participants of FL. Identification of anomalies are mostly done in two known ways. First, by comparing distances between gradients, also known as the model updates. And second, by auditing the test accuracy of each participant's model against the auxiliary dataset. So, the latter is the way used by PDGAN. Now, to the PDGAN. The deployment of PDGAN will be at the central server, where the model updates are pulled together and the auxiliary dataset exists. PDGAN is made up of two main components, the GAN model and the defense algorithm. At every round of FL when PDGAN is activated, the GAN model will be trained over some specified number of epochs, but the defense algorithm will only be executed when the round number exceeds PD active round, which is a parameter predetermined by hyperparameters tuning. PD active round is important to ensure that the GAN model is well trained before it is deployed to be used in PDGAN to defend the federated model. So, the first component is the GAN model, which according to researchers, have shown promising performance in generating high-quality fake images that look genuine. The use of a GAN model is to generate a larger audit dataset from the small auxiliary dataset to audit the test accuracy of each participant's model updates. A GAN model is made up of a generator G and a discriminator D. Both G and D play an adversarial game where G attempts to minimize while D attempts to maximize the same cost function. The GAN model used is a deep convolutional GAN with both G and D made up of many CNN layers. During training, G will generate a batch of fake images from random noise. Then, D will be randomly given a batch of images either from the generator set or the auxiliary dataset, and D will have to determine if they are real or fake. Now, we move on to the defense algorithm, which has three components. Firstly, the audit dataset must be generated from the auxiliary dataset by using the trained generator G of the GAN model. Secondly, each participant's model update U is merged with the current global model G to reconstruct the participant's model M. Then, the batches of images from the audit dataset are fed into each model M to obtain the predicted class labels. As the images from the audit dataset are unlabeled, their so-called true labels will be determined by majority voting amongst all the participant models. Finally, the accuracy of each model M is calculated and the threshold accuracy is determined by setting it at a PD threshold level below the mean accuracy. Then the models with accuracy less than the threshold will be deemed as anomalous and will be purged. The PD threshold is also a parameter to be predetermined by hyperparameters tuning. Purged model updates will be discarded and will not be used in updating the global model. Now we move on to experiments and results. During the course of this project, numerous experiments were done using the CIFAR-10 dataset both before and after the PDGAN was implemented. The FL parameters used in training the federated model for these experiments are as follows. This is the default configuration from the base code. Note that the number of participants in each round is 10, and the percentage of adversaries in the FL system is 10 out of 100, which is 10%. The first experiment was the control experiment, which was done at the start of this project. This was to test out if the base code provided for this project was functional and had no error in training FL. Unfortunately, there were several errors that had to be resolved, but I shall not go into the details. So, the following results were obtained. The blue curve is the accuracies obtained from comparing the predicted class labels to the actual class labels, while the orange curve is the same, but the actual class labels were backdoored. It can be observed that the normal curve flattens off at about 50% accuracy at around epoch 300, while backdoor curve rises to at least 90% accuracy before flattening off at around epoch 350. This implies that the training of the federated model and the application of the backdoors were both functioning correctly, and that any model defense should be deployed between epochs 250 and 350. After ensuring the base code was usable and correct, PDGAN was implemented. Then, the crucial hyperparameters were tuned, which were the round number to activate PDGAN and the threshold as mentioned before. Each experiment was repeated 3 times to ensure consistency in results. The results for tuning PD active round are as follows. The graphs are plots of accuracy differences between the mean accuracy amongst all the malicious participants and the mean accuracy amongst all the non-malicious participants for each round against the round number. They are zoomed in between round 260 and 360 as the control experiment saw the GAN model ready at only about round 300. For each plot, we choose the round number where the mean accuracy differences were positive and remained steadily positive for the next few rounds. The mean of the 3 round numbers was then chosen as the value for PD active round, which was tabulated to be 282. The results for tuning PD threshold are as follows. The graph is a plot of the effective cost against the threshold. The effective cost of each threshold was derived from the mean of all 3 repeated experiments. For each experiment, the formula for the effective cost is as follows. A miss refers to a malicious participant that PDGAN missed. A wrong refers to a benign participant wrongly purged by PDGAN. And a correct refers to a malicious participant correctly purged by PDGAN. Each wrong purge was assigned a cost of 1, while each correct purge was assigned a reward of 6. This is to discourage the purging of more than 5 participants just to eliminate a malicious one as it will slow down the model training. Each miss was also assigned a cost of 6, which is equal to the reward, so that the resulting algorithm will not favor the idea of not attempting to purge any suspected malicious participants at all. As such, the threshold with the lowest effective cost, which was 18, was chosen as the value for the PD threshold parameter. In the final and concluding experiment, the optimum hyperparameters determined in the previous experiments were used in training a new federated model with PDGAN enabled. The accuracy performance obtained was compared to the accuracy performance of the model in the control experiment, which did not have PDGAN enabled. It was observed that the accuracies for predicting the backdoor test data had successfully reduced steadily over the next 40 rounds after PDGAN was activated and remained low without affecting the accuracy for predicting the normal test data. However, it had to be noted that an upward jump in the normal test accuracies was not observed, which meant that the model accuracy was still not improved despite the use of PDGAN. To conclude, I have presented on the distributed backdoor attack as the attack methodology and the PDGAN as the defense methodology investigated in this project. I have also shared my experimental findings with regards to my implementation of the PDGAN methodology. Some important takeaways are also that attacks mostly occur within the malicious participants and defenses only have the pooled model updates to analyze for maliciousness. To end off, we look at what the future holds for this project. Future work should focus on attack methodologies since a defense methodology has already been implemented. The distributed backdoor attack studied in this project can be implemented. In the middle of this project, I also thought of the idea of implementing a detection evasion mechanism as a form of attack methodology, as existing defense methodologies use only anomaly detection methods to defend FL, and many of them have a 2 or 3 strike policy. This mechanism will work like a malware mutex by poisoning the model only on rounds where the model accuracies are above a certain threshold so as to reduce the chance of being discovered. Also, I have just recently learned about the 51% attack in blockchains, which I believe is highly applicable to FL since most defense methodologies use majority voting, clustering, or other related methods for anomaly detection. In terms of defense methodologies, since the original PDGAN research paper have not yet published their codes due to confidentiality reasons, future works can look at improving the project's code implementation when it is published. Lastly, I chanced upon a research paper implementing a defense called Aurora for collaborative deep learning systems, which can be studied and implemented for FL in future by this project. I have reached the end of my presentation. Thank you.